Okay, this screencast is about isomers in monosaccharides. So, glucose in our blood has the formula C6H12O6, but so do 23 other monosaccharides. How can that possibly be? It's because they are all isomers. So, isomers have the same chemical formula, but something about their structure is different. So when we say same chemical formula, we mean like having the formula C6H12O6. We're talking about the atom count of carbons and hydrogens and oxygens in the case of our monosaccharides. So there are several types of isomers. There are constitutional isomers. In constitutional isomers, they have that same chemical formula. So, for our sugars, C X, H, Y, O, Z. Like they have the same formula where they always have the same number and type of atom. So like glucose having C6H12O6, but they have a different order of bonding. So we have seen these before. They're also called structural isomers. I liked the term structural isomers myself. But they have a different structure or constitution. I like to think of the constitution as how we structure our government. And so these have a different structure altogether. In sugars, constitutional isomers are when two monosaccharides have the same number of carbons, but one is an aldose and the other is a ketose. For example, mannose and fructose are constitutional isomers. So let's look first at D-mannose. So it's, let's start from the bottom of its structure. It's CH2OH. Let's just compare it to D-fructose as we go along too. They both end in CH2OH. Okay, so that's their sixth carbon. Then if we go up one carbon, they have a carbon with H on the left and OH on the right. Having that OH on the right, second from the bottom, is actually what makes them D. Then if we go one carbon up, they have H on the left and OH on the right. Go one carbon up from there, OH on the left, H on the right. I mean, so far, everything is the same. But when we hit the next carbon, things are different. When we hit the next carbon for D-mannose, there's OH on the left and H on the right. And for D-fructose, there's C double bond O. Okay, so fructose right now looks like it might be short two hydrogens, but it's going to make up for it because fructose has CH2OH for its last carbon versus mannose has CHO, which we know really means it's C double bond O and then an H for that aldehyde functional group. So we know that it's an aldehyde because, it's an aldose sugar. Versus fructose is a ketose, and it has a ketone. The ketone was the second carbon from the top, that's C double bond O, versus the aldose is the CHO that mannose ends in. So they actually have the exact same number of carbons and hydrogens. Where it looked like fructose was short two hydrogens on that second to last carbon, those two hydrogens actually appear at its very top carbon where it's got CH2OH, that alcohol. So these are constitutional isomers. They have the exact same carbon, hydrogen, oxygen count, but they have a totally different structure or constitution, if you will. What constitutes them, what functional groups is really different. One's an aldose and one's a ketose sugar. So that's a classic example. Okay, I've got to move myself down here. Let's look at stereoisomers or enantiomers. These are molecules that have the same chemical formula, so the same order of bonding, but different 3D arrangements of the atoms, and the two structures are mirror images of each other. In sugars, as in other compounds, the two mirror images are given the same name, but distinguished by a D or an L prefix. So this was like having D-glucose versus L-glucose. So having these stereoisomers or enantiomers or like D and L glucose. So these molecules have the exact same molecular formula and they have all the same functional groups. They actually have the same order of their bonding. All they differ in is their 3D arrangement in space. So D-glucose and L-glucose are enantiomers. D-ribose and L-ribose are enantiomers. They're exact mirror images of each other. D-glucose and L-ribose are not enantiomers because they are not mirror images of each other. So if we pick another sugar, that won't be the same mirror image. So let's focus on D and L glucose because these are exact mirror images of each other. So we can put like a dotted line that can be our mirror in between them. That's just going to represent our mirror and how we're, I just kind of imagine a flipping, like a handedness, like a hand flipping from forward to back as I'm looking at those two images. Okay, so at the bottom, let's start from the bottom again. We have CH2OH on both D and L glucose. Then if we move up one carbon, if we move up to the next carbon on D glucose, we have H on the left and OH on the right. That's what makes it D, that OH on the right, that's that bottom OH, or second from the bottom, if you will. And then L-glucose, again, we have CH2OH on the end, but if we move up to that next trichiral carbon, we have OH on the left and H on the right. So that's what makes it L-glucose, because the OH is on the left. And then if we move up one carbon on D-glucose, OH is on the right, H is on the left. L-glucose, OH is on the left. Move up one carbon on D-glucose, OH is on the left, and on L-glucose, OH is on the right. And move up one more and D-glucose, OH is on the right, and in L-glucose, OH is on the left. So we've got these precise mirror images. Oh, and then by the way, they both end, of course, in C double bond OH in our aldehyde to be our aldose, right? We want these to be aldose sugars, so they better end in aldehyde groups. So the D versus L enantiomers. In the L enantiomer of L-glucose, we see that OH, that's one carbon up from the end, is on the left. So these are stereoisomers that are enantiomers. What about stereoisomers that are not enantiomers? These have the same chemical formula, the same order of bonding, but different 3D arrangements of the atoms. And the structures are not mirror images of each other. So in sugars, when two monosaccharides have the same number of carbons, the same bonding, in other words, both are aldoses or both are ketoses, but they are not D and L of the exact same sugar. They are stereoisomers that are not enantiomers. So they are not mirror images. So examples would be take D-glucose and D-galactose. These are stereoisomers that are not enantiomers. D-glucose and L-galactose are stereoisomers that are not enantiomers as well. Okay, so let's look at our examples here that are D-glucose and D-galactose. They both have CH2OH on the end. Then they have their next carbon has to have OH on the right. That's what makes them D. So they both have OH on the right on the next carbon. Go up to the third carbon up. D-glucose has OH on the right, and D-galactose has its OH on the left. Go up to that fourth carbon. D-glucose has OH on the left, and D-galactose has OH on the left. So, they're not mirrored. The only carbon that was sort of mirrored was that middle OH was on the right on D-glucose and on the left on D-galactose. But the bottom OH, the top OH that we've looked at so far, these are not mirror images. And then if we go to the next one, on D-glucose, OH is on the right, and on D-galactose, OH is on the right. So when they're both on the right, both on the left, these are not mirror images of each other. And then we have our aldehyde at the top, of course. So these are sugars that are stereoisomers because they have the exact same chemical formula, they have the same order of bonding, but they have a different 3D arrangement that isn't mirrored one to the other. Okay, so again, these are ones with same number of carbons, same bonding. In other words, both aldoses, both ketoses, but they don't happen to be D and L of the exact same sugar. Only D and L of the exact same sugar would be stereoisomers that are enantiomers in terms of monosaccharides. Okay, one final thing to remember is that if the chemical formulas are totally different, for example, let's say you've got a pentose with 5 carbons, right? Pent means 5. And then you've got a hexose with 6 carbons. These are not isomers at all. Those molecules would not be isomers of each other because they can't have the same chemical formula, so they cannot be isomers of each other.